Well, hi there, folks. Mr. Bleeker here. I'm at home nursing a pretty bad back today, but one of the things I thought was important is that we get through lesson 7.1, which is forms of radiation. And if we weren't here Friday, we examined sort of the origins of radiation, and we looked at three forms: alpha, beta, and gamma. So if you don't have the notes, I'd encourage you to talk to talk to one of your fellow students, get caught up on the notes, read over section 7.1. What I'm going to do is proceed from where we were at and then just more or less finish off the lesson. Looking at the Google Calendar, I'm going to zoom in a little bit here. This is where we finish off forms of radiation, and that leads us in, do a little zoom here, into a lab activity tomorrow on half-life, where we look at radioactive decay and how we can determine the ages of things. It's actually a really neat sort of graphing technique. We use it a lot in biology to determine how old not only geological structures are, but how old some things that we uncover on archaeological digs might be using carbon half-life. Zoom out one more time, and you might have noticed, lost it. You might have noticed that the chapter 6 test lands on Thursday because Friday is a professional development day right here. So that's a pretty important end of the week to keep your eye on, and I will attach the study guide as per usual to this item here. Okay, so without further ado, what I like to do when I do these lessons is just working off an iPad here, and I'm just going to turn on mirroring for a moment. Here we go. And we had examined three types of radiation. I'm going to pop out in a minute to an animation that sort of explains them a little bit better. It's one that I looked at and showed to the class on Friday. But I did want to mention, and let's just change this color from red, that this symbol down here actually looks like this is a little bit more accurately drawn. I like to draw it as sort of the upside down fish. So this is alpha radiation. Oops. See if I can fix that. Wasn't as clear as I wanted. Okay, so the first one we looked at was alpha radiation. Then we looked at beta, and this last one is entitled gamma. So what are these three types of radiation? Well, just turn mirroring off for 1 second. There we go. And I'll go here. So when we look at the nuclei of elements on the periodic table, what we see is some of those nuclei become unstable. And a simple way to explain it to you is that the proton to neutron ratio starts to get a little out of control. When you look at something like uranium, uranium 235, uranium 238, they have that element has a lot of neutrons, and in the nucleus, represented by these, we call these all nucleons, if you to be accurate in naming the particles. The red ones, if we call them protons, protons would naturally want to repel. It would want to fall apart, but it doesn't fall apart because there are nuclear forces. You could sort of think of it as almost like a nuclear glue or a nuclear gravity that holds everything together. But what begins to occur is that the proportion of neutrons to protons sort of gets a little, as I say, out of control. And especially with various isotopes, it makes the nucleus unstable. So the glue itself isn't strong enough to hold the nucleus together. In one example, we'll look at uranium 238 here. The nucleus itself becomes so unstable to the point where it emits what we see here. It's called an alpha particle. So if we look at the two red balls there, those are protons, and these blue ones represent neutrons. So the last time I checked, every single one of these has one atomic mass unit. This whole thing weighs 4 atomic mass units. You've lost 2 protons. So you look at the periodic table and you say, what has 2 protons and a mass of 4? And at that point you say, this thing just emitted a helium nucleus. And that's exactly what's happened. So watch that one more time. a helium nucleus is released, and you've got a smaller left behind nucleus. And in this case, if you look on the periodic table and you go back 2 elements, you'll see that thorium precedes uranium. So if you lose 2 protons, you're now thorium. So this is nuclear transmutation. Now, a second form of nuclear decay is when something like carbon 14, this itself has not an ideal arrangement of protons and neutrons in the nucleus. And what will happen is this will undergo beta decay. Now, beta decay is a little different. In the case of beta decay, a misspelled neutron, I gotta love that spelling, a neutron switches allegiance, and it goes from becoming a neutral particle, and instead it becomes a proton. Now, it's kind of interesting because when you think about neutrons and protons, they have about the same mass, right? They're one atomic mass unit. Well, when a neutron switches to a proton, it emits a high energy electron, and that goes flying out of the nucleus. Now, you have to stop and think very carefully about what happened here, because if you gain a proton, you become the next element to your right. And in this case, carbon becomes nitrogen, and its weight is 14. You see, the weight here hasn't changed. It has, when a neutron becomes a proton, it still weighs the same, but it emits that high energy particle. So this is now nitrogen 14. The last one, and we'll go back and review these all in the notes, but the last one is gamma decay. Now, gamma decay is when there's a jostling, the nucleus doesn't fall apart here. This is the only one where there isn't really any change to the nucleus. It's just that it's a very high energy nucleus, and this is what uranium-238 will do, where the particles are jiggling and jostling so much that they emit basically high energy. I was hoping to see it. Just a sec. They emit high energy waves, and what they emit is something called gamma waves. So in this case, I'm just going to mute this here. What we can do, we can actually observe these particles being emitted. Now, if something releases, there we go. If something releases, let's pause, go to main menu. We'll go to carbon 14. Here's a good one. Carbon 14, as it undergoes beta decay, emits electrons. And electrons, when they come streaming out of something like carbon 14, those electrons are negatively charged. So if we set up an electric circuit, if we charge 2 plates, positive and negative like this, what we can observe on the deflecting screen is that the electrons being emitted will be bent. They'll be bent downwards, and they'll glow on this portion of the screen. And this is one of the ways you can determine if something is releasing these beta particles, because they'll sort of bend down like this and illuminate the screen. So when carbon is busy becoming nitrogen, carbon 14 is becoming nitrogen 14, as its neutrons switch allegiance more or less and become protons, it emits that high energy electron, and that is what you see here, which is pretty neat stuff. And this is actually how we detected it. I'll pause that. Now, if we look at something like, we'll look at cobalt-60. In this case, and I'll just pause, you can see that there's no deflection going on at all. So if you don't see deflection going on at all, it's because no positive or negative particles were ever emitted. So cobalt-60 is emitting what's called gamma radiation, and that's very high intensity radiation. And it just goes straight through, and it'll hit the middle of the deflecting screen. And at that point, it's pretty easy to detect. That's extremely high energy electromagnetic radiation. You would need a lot of shielding to protect you from this. Okay, now, if you've heard about radon, it's a natural gas being emitted from the Earth. And it comes up through our houses, and if your house has a good vapor barrier, radon will just go around. It goes up into the atmosphere. It is radioactive gas. Now, when radon is being emitted, um, it's basically this is due to sort of the decay of uranium in the soil, and you're getting radon 222 produced as a result. Now, if you watch this, as that uranium decay goes on, and there's a lot of uranium in the soil, this right here is this is an emission of alpha particles. So alpha particles are basically helium nuclei, and they're positively charged. So in this experiment, what you'll see is alpha particles will bend towards the negative of plate because they're attracted to it. And in this case, they'll illuminate the top of the deflecting screen, which is really what this animation is trying to show you. Here's another one I thought was kind of neat. You can see the address up here, but I'll supply that to you if you're interested. If you look at alpha rays, right, do the alpha ray shooter, alpha rays can't even go through a piece of paper. They're very, very weak. They're just helium nuclei after all, right? Now, when you look, here's an animation. You could see that here's the particle that broke away. Just like I said, it's an alpha particle. So what do we got? We've got 2 protons and 2 neutrons. Okay, that is a helium nucleus, right? And it's positively charged. That's why it bends towards the negative plate in that last animation, because those protons are positively charged, right? Neutrons have no charge. So a helium nucleus is basically like a positive chunk that flies off. But what I need you to be aware of is that this just got smaller. In fact, it got smaller by 2 protons. So on your periodic table, you have to look at 2 elements before it, and you will have what the new identity will be. Okay, so we'll go here. If we look at, I'll just save a little bit of time here. We'll look at beta decay, and there goes that high-speed electron, poof. And if you keep your eye on that proton, that neutron rather, it became a proton, and that's it pulsing right there. So it's just as nice twice. Let's watch that one more time, make sure we got it. Keep your eye on the ball here. There it is, and there's the switch, right? So this is what carbon does when it's radioactive carbon becomes nitrogen, and because it gains a proton, it becomes the next element in the periodic table. And that high energy electron, that's pretty weak. That high energy electron itself is stopped by something like, there you go, the aluminum plate, right? It doesn't penetrate that. Now, a gamma ray, gamma rays here, they're overemphasizing to make a point here. Let's reset. Gamma rays are very high energy radiation, and they'll damage your genetic code very, very effectively. So if we let the gamma rays go, that poor guy in the aluminum plate, the point they're making is that it's not good for your DNA, and there are radiation burns you can get from things like gamma radiation. Not surprising, you can get UV burns, but the fellow behind all the cement was properly shielded. Let's do one more shooter here. So we can send that out again. Cooks the notebook, right? We'll see if it hits the tree. Anything that isn't shielded is basically toast, and that's the point they're trying to make. So I'll just hit reset. The animation here is, here's the jostling that I was trying to show you of the highly, almost hyperactive nucleus. And it's emitting gamma radiation like crazy, and it's trying to get back to a more stable state, but you have to realize that's a pretty crowded house. And this nucleus, it's not unstable enough to fall apart, but boy, the guests at the party are pretty nervous. And you're getting a lot of gamma radiation released. So I thought it was a good animation, so I thought I'd show it to you. Okay. There we go. So I'll go back to our notes. I'll make sure that we finish those off. And you'll be able to get your 7.1, section 7.1 finished off. Okay. So alpha radiation is, you have to keep your eye on the notation for this, okay, guys? It's kind of important because, here we go. Actually, I want this one. right here, what they'll say is that you can use the symbol alpha for this, or you can put in He for helium. What I think is really important for you to keep your eye on, let's switch colors, is that this information here is really important. So your mass is 4 and your number of protons is 2. So I'll highlight the number of protons. I'll just highlight the whole thing like that. That indicates the number of protons. So the top number 4 is your mass. Okay. So again, this is a pretty weak form of radiation. You have to be able to identify these symbols. There's 2 ways of showing it. Okay. This is an example of radium-226. And I think what's most important about this is if it's going to lose, here we go, if it's going to lose 2 protons and 2 neutrons, there's your loss of 4. So now this weighs 222. And here it loses 2 protons. And this is the reason why. Let's just connect the dots there. There's your loss of 2. Which is why this element is now element 86 on the periodic table. So now we're no longer radium. Oh, won't pick that up. Now we're no longer radium. Heavens no. See, now we're radon 222 because radon is element 86 on the periodic table, where this thing used to be element 88. And why might that be? Because here's the missing chunk over here. Here is your alpha particle. So this obeys the law of conservation of mass. You haven't lost anything. Nothing at all. Now this is the example we did on Friday here at the bottom, right? And here is your loss of 4 oops. Let's go back. Here is your loss of 4 mass units along the top, and along the bottom, here are your 2 lost protons, right? All because the equivalent of a helium nucleus flies off. And this is something you can pick up with a Geiger counter. Beta radiation. First off, the notation's kind of important. You have to realize, actually, let's go with that. That in this case, right there, because an electron goes flying off, it has 0 mass, right? Down here, you're probably looking for an atomic number. There isn't one. An electron itself is given the notation -1 because it's not even a proton. So we denote the electron as having a -1. Think of it as a -1 atomic number. Okay. So in that case, there we go. We'll do that notation. Again, please be aware that the symbol beta is totally fair game. So you could either see that or you could see that. So when you see this, what you probably want to memorize is that this would be something like, radioactive carbon-14 becoming nitrogen-14. Now you notice I said 14. Well, the mass doesn't change if you lose an electron. Electrons don't have any really appreciable mass. So here we go. We'll take a look at iodine 131. So I'll highlight the mass. Okay, the mass did not change. Okay, but what we see, and this is sort of the interesting part, is in this case we had a switch of allegiance, right? We had a neutron in this case that becomes a proton. And you guys know what happens if you gain a proton. You go up by 1 on the periodic table. So instead of iodine, oh, I can't get that. I need a new color. I can't take yellow anymore. Let's go into a nice sort of, That would go into green. Iodine, which weighs 131, that's its mass. It picks up a neutron, becomes a proton. So it's the same weight. Neutrons and protons weigh the same. So now, yes, what you have weighs 131, but, here's a big but, it's now xenon. Because xenon is element 54 on the periodic table. Highlight that, 54. And it's all because of that extra proton. So what goes flying off in this case is your beta particle that you see here. So you notice that you have to include this, right? These are the products that you get. So in equations like this, it starts to become a little mechanical, and you look at something like this and you say, well, what happened? Well, if it's going to be beta decay, first off, mass never changes. So in beta decay, what you try to remember is that because a neutron becomes a proton, then the atomic number goes up by 1. And then you have to include, it's very important to include, the fact that an electron, high energy electron, basically flies off. So we're going from mercury in this case, there you go, to tellurium. And this is a form of radiation we can pick up. It's pretty strong, but it's stopped by something as dense as aluminum foil, or aluminium foil, however you would like to pronounce it. Okay? So package 7.1 will have a lot of questions on this. And I will show you something about 7.1. I'm going to lighten the load on the total work that you guys have to do, so I'll remember to do that before I'm finished here. Okay, finally, gamma radiation. Again, the symbol, it's a little bit better here. There's no mass to these waves. Okay, there's no change in atomic number. It has nothing to do with that, but it is pure energy. It's very strong. Okay, little upside down fish. So, no charge, no mass. We saw that with the charged plates. This isn't attracted to either. It'll go straight between two charged plates, positive and negative. Because it's so energetic, it'll go through it. It's only really shielded by lead or concrete. When I think of gamma radiation, I sort of think about how strong X-rays are. Gamma rays are much stronger than even X-rays. There's a table. Let's see if I can go back here. Table back. Let's see. Where is it? Ah, there it is. Push that tray back. So when you look at, let's see if I can, there we go. If you look at X-rays and gamma rays, they're very high intense radiation. Their wavelengths are very tight, so they're delivering energy, large amounts of energy very quickly, which is very bad for our genetic structure. This causes all sorts of mutations and can bring on cancer. It's not good. However, at the same time, we can focus energy like gamma rays on tumors to try to kill them. Okay, so we were at gamma radiation. Here we go. Uranium-238, which is quite unstable. Uranium is the last occurring natural element, and it's extremely energetic. It's got a lot of neutrons, and some of this, you got to realize that you're sort of thinking, well, only one form of radiation can happen with one element. And it's not really that simple, folks. Uranium-238 is one where you can get alpha particle decay, and it's so energetic you can get gamma rays. We're kind of simplifying here for you. So, something like nickel, which has a very energetic nucleus, we call this nickel-60. You notice in the naming I say nickel-60 because you sort of name it after its mass. Right? You're like that nickel-61. And we know that we have to sort of denote the fact that this is energetic. And you'll see this little asterisk right over here. And that is sort of an indication that this is one of those types that gives off gamma radiation. So there you go. Once nickel, once its nucleus jostles around a little bit, it lets off some gamma radiation. It kind of cools off. It sort of relaxes a little bit because it has released some of its energy. It's not a great explanation, but you want to think of it as being energetic and somewhat releasing some of that energy. But again, no change in mass or atomic number. That's pretty important. Here's uranium 238, which is it's got a lot of problems. Its nucleus is really full. Now, if you keep your eye on this, you're like, what happened to uranium here? Okay, so this is one of those ones where two things can happen. So we'll break this down a little bit. First off, I see that an alpha particle has been released. Okay, so that means that uranium, which is element number 92, loses 2 protons. So now we're talking thorium 90. Now that's fine. Because helium has 2 neutrons and 2 protons, then we lose right here, the mass goes down by 4. So you have to get pretty good with alphas, where you notice, okay, mass goes down by 4, atomic number goes down by 2. Okay, and this uranium is not only going to release alpha radiation in this case. We realize, okay, because of the alpha radiation is going to become thorium, it's also going to release gamma radiation because uranium was so, its nucleus is, in this case, 238. Okay, there's uranium 235, for example, folks. So what does uranium 238 tell you? It tells you that it's got 5 more neutrons in the nucleus. This thing is already unstable, and you tried to pack, that many more neutrons in the nucleus. It sort of complicates matters. I think you understand. Okay. So when we look at this is a really common test question. You just want to put this one in your old memory bank. Alpha radiation, stop by paper. Not a big deal. Beta radiation, which is a high energy electron, unlike a helium nucleus, it's got enough juice to get stopped by, well, something moderately dense. In this case, they're indicating wood, but the classic example is aluminum foil. And gamma radiation is it has, it's very high energy, like X-rays. And if you've been to the dentist, you know you need something really dense to slow down that amount of energy. So something like lead or really thick concrete. Voila. I think you get the idea. So, sort of a parting thought, a final table. You've seen alpha, beta, and gamma radiation. There is another form of beta radiation that isn't mentioned in your book. We can talk about it another time, but in this case, it's best to just deal with the beta particles that are electrons. So, ladies and gentlemen, that is it. I think, yes, more or less, I've hit the end of the lecture. I'm giving away a couple of these questions. You'll have a chance to, just a second here, you'll have a chance to work on package 7.1. So you get to see all my apps. It's very exciting. There's one app, no, not Dragon City. One app, this is a neat one. There we go. I like this one. So the 7.1 workbook, this is an app called Sync, by the way. You can think of it a bit like Dropbox, but it's a Canadian company. The 7.1 workbook is quite a bit to it, needless to say. Let me get to the working sections. Okay, this sort of first page here, I want you to fill all this in. Make sure that's done, right? And this table, okay, make sure you do that. I know I'm a slave driver, which is just what's the atomic number, look up the mass. If you know the atomic number, how many protons. I think you folks can figure this one out. We've done a lot of this, okay? This is a pretty standard one, but where I want to lighten the load is here. So when you get to this section, which says pages 286 to 289, you can give me every second question. Okay, so that means you'll be doing questions 1, 3, 5, 7, 9, etc. Okay. I want to make sure that you do that. I want to reduce it a little bit for you guys because we have to push off into radioactivity, which is another set of material. But I think we'll all be fine. Okay, so I'm just going to turn off my mirroring there. And like I say, I'll get rested up. But yes, every now and then your back does get a little sore. I think it comes from moving around refrigerators. Yes. So, ladies and gentlemen, have a good day and make sure you've got 7.1 finished. Ciao.